So I'm going to start it. Hello, everyone, and thanks for the introduction. I'm Zahao from University of Washington, and I'm a third-year PhD student advised by Louise Azi and TQ Chen from CMU. Today, my talk topic is challenges and opportunities of sparse compilers in large language models, which is a hot topic, anyways. So to begin with, I'm going to spend a little bit time on our previous work, the Sparse CIR, which is a compiler on top of TVM ecosystem that supports the sparse tensor algebra for deep learning compilers. So TVM is just a ecosystem that have two levels of IR infrastructures, one for computational graph level and another for a tensor level called tensor IR, which is originated from the Halide project, but later on we evolved it to support more hardware primitives. And both the Relax and TensorI do not have support for sparse tensor algebras. So we cannot import workloads that involve sparse operators. And Sparse TIR was proposed to bridge the gap where we learned from previous work like TACO and MIR sparse dialects that we treat the sparse format as a first-class citizen so that we can use them to construct both sparse tensors and the sparse iteration space so that we can write code in a format organistic way and the compiler will take over the job and generate efficient codes. So here is our overall IR design. We have high-level IR that looks like a TACO mentioned in the previous slide, while the low-level IR of Sparse TIR is just a tensor IR in TVM. And as a high-level IR, we can perform some optimizations that is sparsity aware. For example, the composable format, which means we store different fractions of the sparse tensor in different formats because some of the sparse formats are more hardware friendly. But if we store the entire matrix in that format, it will cause a lot of paddings. So to reduce that paddings, we just use different combination of sparse formats to reduce the fragmentations. And then we enter the lower level IRs where we expose more features that are related to hardware so that we can leverage the optimizations such as vectorization, loop tiling, something like that. And the remaining job are left to TVM compiler stack to generate the target-specific code. And the overall search space of Sparse TIR is a different combination of composable formats and different combination of the schedule primitives specified by user at different stages. Here is a generic compilation flow of Sparse TIR. We are given an original matrix and given an original compute description. And we can analyze the non-zero positions and do a format decomposition. And for example, in this example, we just decompose the original formatting a lot of ER pack formats where each row has equal length. And then the Sparse TIR rewrite the original compute code to the compute code on these sub formats. And then we can use the user scheduling language to dispatch this code to different hardware units. In this way, we can implement some of the optimizations such as load balancing if we make the composable formats load balanced. So yeah, we achieved some good speed ups on the workloads such as relational gather metaphor scatter. We achieved 40 times over the state-of-the-art on CUDA. And the reason because previous work we use a two-stage manner, say first compute, first half it, and then use another operator. This causes an intermediate buffer which needs to be stored in GPU, which incurs a lot of GPU memory consumption, also a lot of more I/O access. And by using Sparse TIR, we can fuse them together and just store the intermediate buffer in shared memory. And we can see that both of our design, the composable formats and using the low-level IR optimization, both of them matters. And yeah, so far so good. I think since last December, I started to look at how can we use the Sparse TIR to exploit the sparsity and to optimize the LLMs. So we found that, there are a lot of opportunities, but the current compiler design are not suitable for them. I'm going to explain why. There are several sparsities. I'm going to explain the activation sparsity, storage sparsity, and weight sparsity. I'm going to start with a mixture of experts, which is the activation sparsity. Mixture Experts is an architecture proposed by Google in 2017, and where the core idea is instead of using a single weight for each layer, it maintains a set of weights. And during execution, there will be a router network that selects a part of them to be activated. So you can see the routing matrix forms a sparse matrix. And previous work such as megablocks, they find that, okay, they design the operation is a sparse operation, and they design a set of very efficient operators to optimize them. We find that, okay, this workload is very similar to the relational gather metamal scatter we mentioned before. And we have very good schedules for it. But unfortunately, our schedules are proposed for stationary sparsity, which means the same sparse matrix was used many times. So we only need to compile once and use several times. But unfortunately, in Mixture of Experts, this routing matrix was produced in real time, so that we need to recompile each time we encounter it. So that is not desirable because compilation time is not negligible. So our solution is that we just factorize the scheduling space. In the later stage of the IR, in the loop level IR, we decouple the space into outer space and inner space, where the outer space is maintains a symbolic shape, and we split it by a factor of a static shape. And in an inner space, the entire block size is just a static shape, so that our solution is to doing auto tuning for the inner space, where the shape is fully static. And for the outer space, we just do some naive scheduling, such as just mapping to physical thread or doing sequential execution. It turns out such solution works good, and we can achieve very similar performance for fully auto-tuning this workload, while we do not have a lot of compilation overhead. Another sparsity I mentioned is the storage sparsity. This is what we encounter during the optimizing the large language model serving. Actually, if you are a company that serves large language models, you will find that if we serve a single request at a time, it is very inefficient because the hardware units will not be fully utilized, and the operational intensity is so low, and batching can help in this case. If you look at this figure, we can see that by increasing the batch size, we can increase the throughput by 8 times, while only increase a little bit on the inference latency. So batching is necessary for serving, but for large language models, previous systems, they only batch the MLP layers, which is just concatenating the sequence of different lenses from different requests and do a matrix multiplication. And for self-attention layers, their solution is just execute them one by one, which is okay, but we use NVIDIA profilers, we found that, okay, the self-attention time is not negligible. If we batch the MLP layers, the MLP execution time would be very little, but a lot of fraction of time will be spent on self-attention. So we turned to Sparse compiler for help. Actually, doing the large language model inference, batch language model inference, the query is just a multidimensional dense matrix, and the key and values can be viewed as a regular tensor. Say one of the dimension is the length of one of the dimension depends on which request it belongs to. So we just write a flash attention kernel on top of this query and key value matrix and use sparse BR to optimize it. The challenges we met is the same as a Mixture of Experts, which is a dynamic shape issue, and we use scheduling space factorization to solve this. And we found that after we batch in the self-attention layers, we can reduce the time to a little fraction, so which can greatly increase throughput while reducing the latency. Another kind of sparsity, the weight sparsity, mainly come from the need of localizing LLMs. We know that nowadays, large language models are dominated by large companies, and when you use ChatGPT, you are not running it locally. You are just running it's just running on the cloud of OpenAI servers. But why do we need local LLMs? So we think that it is still important to have local large language models because people have many personalized data, and they do not want to reveal this information to these companies. And also, we can just Also, we can just build a personal assistant according to our user experience by doing localizing. The major bottleneck of localizing large language model is a lack of on-chip memory. You can look at this figure. The scale of large language models grows exponentially during the years. But actually, the commodity software have limited memory. I would say M2 Ultra might be the largest so-called commodity software. It has 192 gigabyte on-chip memory. It cannot serve 175 billion models if we do not do anything. And if we use gaming GPUs or mobile, the on-chip memory is much smaller, and we can only use the state-of-the-art models years ago, which is far from the performance of the ChatGPT these days. So the most frequent approach people use is quantization, which means, we instead of storing the matrix in 16 bits, we just quantize it to 3 bits or 4 bits. If you count for the scales, it will be 3.5 or 4.5. In this way, we can increase the bar. Say, for each company's hardware, we can afford to run in a larger model than before. But there is another classic way to reduce the parameter size is called network pruning. But why it is not used now in large language models? The reason we say we categorize the reason as curse of bits. Here's a figure of the classic pruning algorithm. What they did is to iteratively apply a sparse mask, and after we apply the sparse mask, we update the weights by retraining the whole model on this sparse mask. And doing this iteratively, it can achieve 10 times parameter reduction, which is good, but it is not affordable for large language models. They always do this for some small models such as computer vision before, which is affordable to retrain again and again, but large language model is too costly. So people propose one-shot pruning algorithm, which means instead of retraining the whole network again and again, it just optimizes parameters locally. Say, for each layer, we suppose the weight is W, we're trying to optimize the mask matrix and updating weight for it. And in this way, we cannot achieve the same level of parameter reduction because we do not have global optimization information, but we can still get decent reduction. Say, in the Sparse GPT paper, they mentioned that we can get a 16% sparsity at nearly no performance loss. But 16% sparsity is very embarrassed when used together with quantization. Because if you look at the CSR representation, you can see that the values are stored in 4 bits, but we need 16 bits to store in the indices. So one index is worth 4 values. And people might say we use relative indices or we use Huffman coding to compress it, but unfortunately it doesn't compress it so much. So the indices would still be the major bottleneck. So the solution we use for this is a bit mask. Say we just use 0 or 1 to indicate whether there's elements here or not. It is not efficient for hyper-sparse matrix asset graphs, but good for the network pruning. And in this way, we can further compress large language models from 30 gigabyte to 1.7 gigabyte. Can we go further? Yes, of course. If we look at a more structured matrix, we can just use in some lookup table to store the different combinations and compress them to lower than 1 bit. Or if you look at block sparsity, it will be much better. And also even the structure matrix such as butterfly matrix and monarch matrix, and the pattern is fully fixed so that we do not need any bit to store it. But we need to pay the price. You can look at the figure from the Sparse GPT. If we post more restrictions on the sparse format, so the performance would be worse. So I think it is an algorithm developer's job to develop a good algorithm for network pruning. What we compiler people do is that we should allow them to customize the encoding and decoding scheme. And actually, what we did in Sparse compiler could be, Sparse CIR could be categorized as supporting the encoding and decoding for the compressed indices in CSF manner. And actually, quantize is another sort of encoding and decoding. So I think in the future, we need to unify this representation, just do a unified compression and decompression framework to support a combination of them so that we can leverage ultimate compression for large language models. And a shameless flag here, MLCLM is a compiler solution for us to deploy the large language models locally. And you can try it out on your mobile without connecting to internet. So conclusion here is that for activation sparsity and storage sparsity, we need to support symbolic shapes. And to address the curse of bits, for compiler developers, we need to support customizing encoding and decoding scheme. And for algorithm researchers, they need to optimize the overall number of bits, but not just sparsity. And here's a link to this MLCLM project and the Sparse CIR. If you want to know more about Sparse CIR, you can check our S+ paper this year. Yeah, that's all. Thank you.